In this video, we're going to begin talking about light and specifically illumination. The main idea of this video is that light rays travel in straight lines and can change direction only when they encounter a boundary. Two essential questions we're going to answer are: what is a ray model of light, and how are distance and illumination related? Vocabulary that we'll review are terms like precision, and then new terms like ray model of light, luminous source, opaque, translucent, transparent, luminous flux, and illuminance. So light's path and the ray model of light. So we say that in the ray model of light, light is represented as a ray that travels in a straight path, and the direction of which can be changed only by placing an obstruction in that path. So light is going to continue on and propagate in a linear fashion unless something is in its way. For instance, some type of boundary here, or whether it reflects off that boundary, or maybe it goes through the boundary like a piece of glass or something like that. And so in this chapter, we're going to assume, for the purpose of simplification, that all light sources are point sources. Now, in reality, they're not always that way, but just to simplify things, we're going to consider light as a point source. So rays of light come from sources of light. One of the biggest sources of light that we encounter in our everyday life is the sun, and that's what lights up our day. And we use that light for all sorts of things. And even when we talk about the sun, we're going to consider that to be a point source because it is so far away. Even though the thing's huge, but it's so far away, we'll consider it just to be a source of light at a single point. And objects such as the sun that emit their own source of light are called luminous sources. So the sun creates its own light. It is a luminous source. It creates the light that we can see. Objects that you see due to light reflecting from them, such as the moon or such as trees as you walk around during the day, those are illuminated sources. So we see objects because light is coming off of them and into our eyes. But not all objects are creating their own light. Things that create their own light are luminous sources. Things that are just reflecting light are illuminated sources. Of those illuminated sources, we have ways that we can classify them. So a medium such as a brick that does not transmit light but reflects and absorbs the light, we call that opaque. We cannot see through brick, but we do see the bricks. So the bricks are reflecting the light, that way we can see them, and they sometimes absorb some of the light, especially if we see a color of the brick, or if they heat up in the sun, they're absorbing some of that light. So those objects are opaque. A medium that transmits most light, such as air and glass, we call those transparent because a lot of the light is able to come through. And then the medium that's in between that transmits and reflects light but does not permit objects to be seen clearly through them, such as frosted glass, we call those translucent. One of the key things to remember here is that transparent or translucent media not only transmit light, yes, light comes through, but they also can reflect light, or at least a portion of the light. Think of a windshield on a sunny day. You'll see some light reflect off of it, however, you can see light go through it as well. So you're going to get a portion reflected, and it is also transparent. Now, let's take a moment to talk about the quality of light that we see. So with the ray model of light, a source that is brighter produces more light rays than a less bright source. So when we represent this light source, we're going to draw more rays on it when it's a brighter source. And the rate at which light energy is emitted from a luminous source is called the luminous flux. And we represent that with P. And so the luminous flux, that's telling us how much energy is coming out of that light. So the brighter the light is, the more luminous flux that it has, more energy is coming out. The unit that we use for luminous flux is called a lumen, or we signify that with an LM. Sometimes when you buy light bulbs in the store, you'll actually see a unit. It'll tell you the number of watts, and sometimes I'll tell you the number of candles, and it might even tell you the number of lumen. And so this is all talking about the energy that it's going to put out over a region of time. And the luminous flux falling on a given surface area at any instance is called the illuminance. So the luminous flux is coming from the source, and then that energy is hitting a surface, it's illuminating a surface, and we call that the illuminance, and we give that the letter E in our equations. And we measure the illuminance in lux, or we use Lx, which is equivalent to lumens per square meter. To increase the brightness that you experience, you could either use a brighter source, which increases the luminous flux, or you could move closer to the light, decreasing the distance. And so a point source illuminance is going to be given by the equation that E is equal to P over 4 pi r squared. Now this comes from the surface area of a sphere because all point sources propagate out in spherical wavefronts. But P being the luminance, the luminous flux here, the source, and E is the illuminance, that is equal to the luminous flux divided by 4 pi r squared. So if we decrease the radius here, then that's going to increase our illuminance. That's going to appear brighter. So the closer you get to the source, the brighter it appears. The greater the luminous flux is of that source, the brighter it appears. And the luminous flux of the light source is spreading out in all directions, so only some fraction of the luminous flux is available to illuminate the object. We can only use this equation if the light strikes perpendicular to the surface it is illuminating, and the luminous source is small enough or far enough away to be considered a point source. So when we're talking about the sun, even though the sun is very, very big, it's a good enough distance away that we'll consider that to be a point source for our calculations in this class. So let's take a look at an example. You shine an 8 times 10 to the second lumen light bulb onto a person who is standing 2 meters away. What is the illuminance of light on this person? So we want to know how bright basically is the light that's reflecting off of the person. All right, so think of the illuminance. If you're shining a very dim light on somebody at night, or the sun is shining on that person during the day, you can see the reflected light off that person very differently. And so that's what this illuminance tries to quantify. And so we want to find, well, how much is this person being illuminated? So we want to look at the situation, and we see that we have P that is given, that's our luminous flux, and we have a distance of 2 meters. We're looking for E. And so this person is 2 meters away from the source, and we can assume that the light bulb acts as a point source, just to make things simplified for us. Plug this into our equation, and we get 16 lux. Now, I know that 16 lux might mean absolutely nothing to you, and that's fine. It's not a common unit that we use in everyday life. However, it's just something to give us some reference. So when we're comparing these illuminants, we have a way to quantify how brightly lit something is. And we can look at this, and yes, the units do check out, and so all the positives are, or all the quantities are positive, as they should be. So don't get too wrapped up on the units that were introduced in this video, because they are new, they are a little unique. However, it's just an attempt to quantify something that you already observe and see in things that create their own light and things that reflect light, and being able to quantify those two concepts there. Hopefully from the video you're able to have a brief understanding of what the ray model of light is and how are distance and illumination related. Thank you.